So welcome back for the first reading group talk for 2025, and hope everyone had a nice vacation and have some time to rest. So we are very excited to for today's speaker, Michelle and Filippo. So today they will be presenting interpreting temporal GNNs with Koopman theory. And for a bit on our speaker, so Michelle is a PhD student in the Department of Mathematics and Statistics at UiT, the Arctic University of Norway, and he received his master's and bachelor degree in physics from University of Padua, Italy, and his research spans from uncertainty quantification to interpretability for randomized and trainable methods on time series and graphs. So I'll hand the mic to you.
Okay, thank you for the introduction, and hi everyone. Yeah, thank you for the opportunity to have this talk.
Yeah, no problem. And for any questions, do you prefer us to interpret you during the talk or save at the end?
No preference. So if it's really important, I guess you can also interrupt me. It's fine.
Okay, sounds good. Thank you.
All right, yes. As Andy was saying, I will talk about, my talk is titled Interpreting Temporal GNNs with Koopman Theory. So let's just dive in. The outline of, sorry. Yeah, the outline of my presentation goes as follows. So I will first talk briefly about temporal graphs. I assume that everyone already knows a lot about them. Then I will talk about the specific spatial temporal model that we used in our work. Then I will give some details and some information about Koopman theory and how we applied it to interpret the model output. And finally, I will offer some future directions for further work. This presentation is based on this paper, on this preprint that you can find already in archive that I made with my co-supervisors, Filippo and Simone. So let's get started. So the definition we used for temporal graphs is the following. So we consider overall set of nodes, a global, let's say, set of nodes, B. Then we consider a set of edges, and we define the temporal graph as a sequence of graphs, basically. So at each time step, we have that the topology can change. So in the video, you can see that at each time step, only the edges that gets highlighted in red are present in that at that moment. And as usual, on each node B, we equip each node B with a feature vector of dimension RD. And also that feature vector is assumed to change with time. So in the video is the color of each node. And you may have noticed during the animation that some of the nodes changed color. As a model to model this type of input, we used we considered a standard architecture made of two components. So a graph convolution network that learns patterns and process the spatial structure of the input. So it's usual, as in the animation, is a message passing mechanism for each node. And then once we have an embedding for each node produced in this way, for each time step, we then process the temporal component of the input with a recurrent neural network. In our case, we used an LSTM. This at the end, then we produce in this way an embedding for the whole temporal graph that we can then use for our downstream task through a simple MLP as a readout. This type of model offers some challenges for the interpretability purposes. Our goal is, of course, to interpret this type of model. In our case, we have two sources of complexity. So one is given by the model itself and the input that has this non-trivial interaction between spatial component given by the topology of the graph and temporal component, so the time dynamics of the graph itself. And then, as usual, of course, being a neural network with graph convolutions and OSTMs, this, of course, comes with its own bargain of difficulties to interpret with all its nonlinearities. So this is for, let's say, the temporal graph part. Let's now have a bit of excursion on Koopman theory. You may be familiar with dynamical system. So let's consider the most basic example of a dynamical system, a discrete dynamical system. So where we have a state, the state of the system xt, that evolves with time according to some dynamics f. The usual approach to study this type of system in dynamical system theory would be to find, for example, fixed points, and then maybe try to extract some local information by doing some linearization locally around fixed points, this type of techniques. Koopman theory instead offers a different approach. What Koopman does is he suggested introducing a space of observables, so a space of function phi from the state space of the system to C or R. So this is an infinite dimensional vector space of functions. And he suggested to use this new space as the new state space of the system, basically. And in doing so, with this trick, you can define an operator, Koopman operator, kappa, which acts on this space of function phi by pushing it along the dynamics of the system. So kappa of phi of xt is equal to phi of xt plus 1. Why would you do that? Well, because you can easily verify that such an operator kappa is linear on this space, and this is quite nice. So we started from a dynamical system as like ugly and nonlinear as you like, and with this simple trick, you are able to translate it into another dynamical system on a different space, whose dynamic is instead linear. And to give you a bit of an intuition of why does this work, I have a simple textbook example that maybe will give you a better idea of what's going on. So if you consider this simple two-dimensional dynamical system, which is nonlinear because there is this quadratic term here, there is an easy trick to transform the system into a linear one. You just introduce an extra observable, an extra variable, z, defined as the square of xt, and then you can easily check that the dynamics of z depends on z. So you are able to introduce this extra variable, and the system is still closed. You start with 2 variables and you end up with 3 variables. And in these new 3 variables, the system is linear. Of course, this is a naive example. You can't do this in general for any system. This is a very specific example where you are able to close this system of equations by introducing an extra variable. But the idea behind Koopman theory is the same. So you are introducing extra observables that are nonlinear. In this case, it's a quadratic function. But you add more, potentially infinite. And Koopman theory tells you that on that space, the system becomes linear. So to sum it up, the nice thing about Koopman theory is that it translates, so it moves you from a local description of a dynamical system to a global one, because we don't need anymore to focus on locally on some portion of the state space. Also, the dynamics is, of course, linear, as I showed you. The cost of this operation, of course, is that you move from a finite dimensional state space that you have at the beginning to a potentially infinite dimensional one. So, of course, it doesn't seem that you gain much. You get a simpler description, which is linear, but on an infinite dimensional state space. So, what's the advantage here? The nice thing about Koopman theory is that throughout the year, many algorithms were created, related, somehow linked to Koopman theory. And they're all data-driven algorithms that somehow make use of these concepts to study dynamical system. One of these algorithms is dynamic mode decomposition, which was actually formulated first in fluid dynamics, and only later on it was rediscovered in connection with Koopman theory. A dynamic mode decomposition is, again, a data-driven algorithm, a data-driven method that allows you to study a dynamical system from its trajectories. So the idea is that you take a trajectory of the system, x of t, and you define these two objects. So big capital X is collects all the data points of the trajectory from x1 to xt minus 1. And capital X prime is just the time-shifted version of X. The idea behind dynamic mode decomposition is that you can approximate the Koopman operator by doing a simple linear regression between x and x prime. So this operator C that is given by this algorithm allows you to transform the x, capital X, and move it one step forward into x prime. And it was later shown that this does indeed approximate the Koopman operator kappa. What is actually dynamic mode decomposition used for, so DMD? Sometimes it's used as a simple dimensionality reduction method, for example, because once you have, DMD provides you with the eigenvectors and eigenvalues of this approximated Koopman operator. And once you have those, you can expand your trajectory or the state of the system into that basis. So the eigenvectors are also called DMD modes. And the idea is that DMD allows you to find these DMD modes that are that express some nice spatial pattern of your system. And you can then evolve them with time quite easily by knowing the eigenvalue. And so you can also distinguish basically in which directions the motion of the system is oscillatory, for example, or with an higher frequency or lower frequency, where the dynamics is slower or faster, you can decompose your signal in this way. And so you can analyze, because these DMD modes may provide some insights on the system itself. So this is one of the algorithms based on Koopman theory that we used. Now let me introduce the second one. The second one is called sparse identification of nonlinear dynamics, or SINDY in short. And actually, this algorithm was born in the context of discovering the equation of motion of a system. So SINDY is a method that allows you to find the equation of motion of a system starting from trajectories of the system itself. But we actually used it in a bit of an original way as an explainability tool, as I will show you later on. So the idea behind SINDY is a bit the same as Koopman theory. It's strictly connected with Koopman theory. You want to enrich the state of the system by adding some nonlinearities. So you define a library of nonlinear functions, theta of x, where x is still the trajectory of the system as before. And these library may contain, it must be specifically tailored and designed according to the problem at hand. So it may contain as many nonlinear functions as you want. And then SINDY assumes that you can describe the dynamics of the system with this equation. So the state of the system, the next step is a linear combination of these nonlinear functions of the state of the system. So psi is a vector that you get from sparse regression that will select which of these nonlinear components are more relevant for the dynamics of the system. And this is why this is a method to, again, to discover equations of motions from data, because you get this equation. So now that we have a bit of a background, I can show you how we propose to use these methods and these algorithms. So the idea, the starting point of our work is realizing that the model that we are using, so the temporal GNN, it's basically describing dynamical systems, because we have for each time step an embedding of the input temporal graph. The idea is to analyze this dynamical system using the machinery that I just described, coming from Koopman theory. We can't just simply apply DMD to this embedding, because DMD, of course, relies on the assumption that the dynamics is approximately linear, and of course we have no chance that this HT will evolve linearly. So what we did first was to modify slightly the model. So by adding some extra trainable parameters and some extra loss terms. So we defined a new internal embedding of the model, H tilde. And we define in such a way that it's by definition, by construction, a linear transformation, a linear evolution of the original embedding of the system, where this capital K is a trainable parameter and will take the role of the approximated Koopman operator. So we trained the model not only by training it on the final task, the classification problem at hand, but we also train it in such a way that the evolution, we push the model to learn a representation of the input h that evolved linearly with time. To do that, we add these extra two loss terms. So the first uh, is simply pushing h tilde also to hold some meaning. So it also has to provide the correct output. And then we also add this observable loss that, well, there is a regularization term on kappa, on k, but then there is also this mean square error that pushes the original embedding to be as close as possible to h tilde. So this term ensures that the model learns to represent linear dynamics of ht, because h tilde evolves linearly by definition. So in doing so, we are encouraging the embedding of the system to evolve linearly, just as h tilde does. The final loss function is like this. So the original loss, in our case, we are considering a binary classification problem. So we have this binary cross entropy. And then we have the extra two losses that I introduced before. And basically, introducing this modification into the neural network is a quite standard approach to basically force the model to represent a Koopman observable. So the model is a Koopman observable that allows for a linear description of the system. In a way, you can see it in that way. So the questions that we want to ask them is if there is a way then to use all these machineries to do explainability. So to study the dynamics of the system and do some explainability on what the model learns to recognize in the input. So in particular, since it's a temporal graph, we want to focus on temporal explanation. So we would like to get a time weight out of DMD. And then we would also like to have some spatial explanations that can be declined as a node explanation, a node level explanation, so that tells us which nodes are most important. And also an edge explanation, so which edges are more important for the output. To do this, so for the first 2 points, 1 and 2, we use DLD, and for the third one, we propose to use SIMD. And we do it like this. So we consider projections of the states of the model onto the Koopman modes, so the eigenvectors of the Koopman operator. And we argue that in those directions, these projections must hold the information, the fundamental information that the model was able to recognize in the input. That information must be encoded here. So from this projection, we define the explanation weights. We define the temporal weight simply as the derivative of this signal, and then a node weight that is just a distance from the average value, let's say. And then using SIMD, we can also define a weight on the edges. So the idea here is that, again, this is the equations that I showed you before that SIMD provides, applied on the states, on the embeddings of the model, H. And we fit SIMD by finding this psi parameter. And here we have, we can decide how to build this library of nonlinearities. And we use this liberty which could be seen as a flaw of the system because it's a bit arbitrary. But in our case, we use this arbitrary aspect of simile to our advantage because we know that the dynamics of the node n must depend on, more importantly at least, on the dynamics of the neighboring nodes. So we already know in a way, like we can already point at which edges should be more important. So we can enforce this bias when defining Cindy libraries by only adding terms that depend on neighboring nodes, basically. And when we fit the psi parameter, that parameter will tell us which of these monomials are more important for the dynamics of n. And implicitly, it will tell us which edge is more important for the dynamics of n. In particular, we build this library by considered, as I said, monomials of couples of neighboring nodes to keep it small enough. And using this psi then, that at this point holds the information about which edges are more important, we can define this weight on edges as simply by summing over all nodes and summing over all those couple of nodes that are, let's say, all those monomial terms that refer to the same edge, basically. Let me show you the results of these of the experiments we performed. So first, let me talk about the data sets we used. As I mentioned earlier, we focused on a binary classification task. And the input temporal graphs that we used are as shown in the videos. So they were all data sets with a real topology. So the time-varying topology of these data sets were real, coming from different contexts, while the dynamics of the nodes on top of that, that was simulated with an SI process. And these data sets, so these temporal graphs were split into two classes. So the task was to distinguish which temporal graphs were undergoing a dissemination process, so an infection process, if we want, or not. The point, like why we selected this data set, is that we had ground truths. Since the node labels were simulated, we had the ground truths for explainability, both on the time that an infection occurs, which nodes are involved, and also the edges. I have the table of results here, but I mean, you can check that also on the preprint itself. So the first two rows, they are measuring the time quality, let's say the quality of the time explanation. So it's an F1 score between the time weight provided by our method, by DMD, and the ground truth, while these four extra rows are the area under the curve that measures the quality of the spatial explanation, both on edges and on nodes. Now, instead of commenting on these results without too much context, I will show you one instead. So in this plot, what you can see, so the red line is the ground truth. So that highlights those moments, those time steps where an infection occurs in this specific case. And the color background, that is the explanation, basically. So the more yellow it is, the more important that moment is. And you can indeed see that there is a nice match between the two. Uh, Here I show you the explanation on nodes. So here in the bottom left corner, there is the ground truth. So those 5 red nodes are those that get infected. So those that are involved in the dissemination process. And indeed, the explanation mask correctly highlights them. And last is an example of explanation on edges. Maybe the color scale is not the best here, but the ground truth again is this edge here. And this edge here is indeed the one with the highest score. I think in this example, the area under the curve was actually 1. Now, a nice thing about this approach is that so we have an explanation over time, so we know which times are more important for the model, and we know which nodes are more important. And actually, we have this information on nodes at each time step if we want. So we know when each of these nodes became important for the model. So we can combine these 2 information together and create a video explanation if we want. So here on the right, you can see the ground truth and the starting infected node, and that the infection spreads, and with a bit of delay, the explanation correctly highlights the infected nodes, well, with some spurious nodes here, but it's quite accurate. Now, I will briefly talk maybe about future directions, what we're working on right now, and what are possible future works from this. So we worked on comparison. This is not in the preprint yet. We have yet to add it. But we compared it. There are not many explainability methods for this type of problems, but we figured we could use a simple saliency method that, of course, doesn't take into account the topology. Uh, and well, the results depends on each data set. Sometimes saliency can provide better result. This is for the node explanation. Some of the times not. But this at least give us the, let's say, a reassuring message that our method is indeed providing solid explanation. And of course, one comment that I have to make here is that with saliency, still, you can't really produce an explanation for edges. So this is only comparing the time explanation and the node explanation. Another thing, other things that we will consider or we may consider, a first point could be to consider more spatiotemporal models. In the end, we can apply these methods to a model if that model provides us with an embedding at each time step, because then that defines a dynamical system that we can analyze with this type of techniques. And we are indeed working on another model structure other than what I presented. So a diffusion convolutional RNN. Another interesting thing could be to use other DMD variants. There are a lot of them adapted to all sorts of different scenarios. So it could be, we used the most basic one, let's say the original one, but it could be nice to compare them and see if there is a difference. Another interesting aspect that I'm working on is to consider different tasks in general, in particular, moving away from the binary classification problem that may be maybe a bit too simple. So maybe a classification problem with more classes could enrich and make it even more apparent that these methods actually work and provide valid insight. And then, yes, maybe even go beyond classification problem, maybe consider well, anomaly detection could be one, but also forecasting maybe. That remains to be seen. So yeah, thank you for your attention, and yeah, I'm open for questions.
Yeah, thanks for the great presentation. If you have questions, feel free to leave them in the chat. I think it's super interesting. So I have some like clarification questions, mainly on how you run the experiments. Yeah, and also like super nice slides. Don't know how you make the animations, but looks very nice. Um, so for the experiment, so for the infection process, do you use something like the SCR model or um
Um, I'm not sure what that is, but let's say the infection itself, that is like that's the input. I didn't simulate the data. I took these data sets that
I
were
see,
already made it, so I didn't bother. I can't go back fast enough. I didn't bother doing that.
I see.
About the animation, so those are done with the Manin library done by the YouTube channel Two Blues One Brown. If you want to check that.
Okay, that would
Uh,
be cool. If you can share the link to the chat. But um, yeah.
oh
So
yeah,
I have
sure.
some questions. Um, so for the results, so you are basically evaluating if it predicts if it's the correct like true infection or it's a random noise. Is that the
Uh,
task that you see?
yeah, maybe I didn't give enough detail. Let me see if I find the right. A bit slow my laptop at the moment. Uh, Maybe I can find the slide with the description. But anyway, the two classes. So one class is made of those temporal graphs where there was the infection process was simulated. So that's
Mhm.
one class. So
Yeah.
infection process. In
Mhm.
the other class, what they did was to at each time step, so they would consider a temporal graph where the infection was occurring, uh, and uh, um, they would shuffle the nodes around. So they at each time step, they would take the nodes that got infected and they would shuffle them. And so this is the second half of the data sets. Uh, so in one class there is an actual diffusion process. In the other one is it's simply yeah, it's a random process. Let's say. I don't know if that makes sense.
Maybe I can just add one thing
Yeah.
that in the first class, another node can become infected only if it's like in contact with another node.
Right.
So there is an actual SIR process.
Yeah. Yeah.
This one for modeling like
Yeah.
susceptible
That's what I was
infected
asking. Yeah.
record. Yeah, exactly. So
Okay.
that's like a proper diffusion process of some infection. The other just one node can become infected at random at some point.
I see. I see.
Okay. Not
Uh,
out of control. Okay.
and for the model, does it only depend on T minus one, or does it depend on all the previous trajectory? So for the dynamical system that you use here.
Um, you mean when I fit the Koopman operator into it, or
Yeah.
the
Yeah.
uh, well, okay. In the naive, let's say in the simple version of DMD, I don't know what's happening with my presentation. Okay. In the simple version of the MD, yes, you have a simple linear regression between x and x prime, as I showed earlier, where x prime is shifted by one time step only. Um, in more sophisticated version of DMD, you may have different things. You may add, for example, there is extended standard DFD where you add nonlinear functions on top of that. So you consider state X, but also you consider other nonlinear function of X to enrich the state. But yes, in our experiment, yes, there is only one step.
So basically, like first order Markov assumption. You're assuming your
Yeah.
past only depend on the immediate, well, your future depend on only on the immediate.
Yes, and as I mentioned during the presentation, that assumption didn't hold. By simply using a trained model alone, I had to enforce that linearity in the model itself while training.
Right. Okay. Yeah, so I still have more questions, but is there any question from the chat or from the audience?
Maybe just one additional clarification, Andy,
Yeah.
that the underlying model, of course, can depend on as many time steps as you want, right? Because it's a time and space model in this case, so it kind of depends on all the previous time steps. But it's the explanation which has this sort of dependency only on the previous step.
Yeah, because I was thinking that sometimes you can have causal structures on temporal graph that spans over multiple steps. So let's say timestamp 1, A becomes friend with B, and then timestamp 2, B becomes C, and then timestamp 3, now because it's closing the triangle, so now it's predicting that edge and these kind of things.
Yeah, in this case, by construction, the infection process was simulated only by neighboring nodes. So yes, in more complicated scenarios, you're right.
It's a good, interesting point, this one. Yeah, thanks.
Yeah, thank you. Yeah, so thanks for the great presentation. Yeah, so I think it's a very interesting direction in like interpretability for temporal graph. I'm not sure even this is used in static graph before. So I think this is a very like exciting new research direction. So looking forward to seeing more preprint and more research from your group. Yeah, and let's thank the speakers again.